So as Stephen mentioned, my title of the talk is Modeling Stock Market Data Using a Stochastic Model. So basically, this is the intro, the outline of the presentation. So we will begin by looking at, the introduction, trying to, let you know the background of the stock market data and also stochastic differential equations. And then we'll be looking at the methodology. Right after the methodology, we will discuss two applications, and then we will discuss the results and look at some conclusions. So now, due to the advancement in technology, there has been, huge amount of data which is now readily available, unlike, previous years where it was very difficult to, get data. And because of the fact that right now we have huge amount of data sets, uh, practitioners and researchers always want to be able to make informed decisions from the data. And how can they make informed decisions? This can be achieved by analyzing the data sets. Okay, and it's not only about making informed decisions. Most people are also interested in prediction or forecasting, the data set. So basically, that's what people are so much interested in, the ability to make informed decisions from the data. And because we are talking about the enormous availability of data, something that comes to mind is big data. And I believe most of you might have heard, that word, big data, a data which is big, right? Well, actually, that's not true. Big data means that a data set which, cannot be analyzed by using the traditional, models. Okay, so uh, basically, if you have big data, then we are talking about complex data sets which needs more advanced, tools in order to be able to analyze it. And I should say that uh, for a data set to be considered big data, it needs to satisfy four properties. Okay, and the first property is volume. So what do I mean by volume? So basically, the volume means the dimension of the data set. Okay, it should be a multi-dimensional data set, meaning that you have several observations, and then for each of the observations we have several measurements. Okay, so we're looking at a huge dimension. And then the next property of big data is velocity. So basically, velocity talks about the rate at which the data is generated. So for instance, it ranges from second, it could be minutes, it could be hourly, it could be weekly, monthly, quarterly, or yearly. So then, basically that, represents the rate at which it's generated. But most often, the common rates at which they are generated are, either it's second or minutes. Okay, so normally if a data is generated secondly or minute, then that data is known as high frequency data. Okay, so basically that's what we mean by that is a data which arrives at a more frequent time. So we're looking at second or minute. And the next property is variety. And what we mean by variety, you notice that for data can come in different formats. Okay, it could be textual, it could be numeric, it could be audio, it could be video. Okay, and so basically, variety talks about the different formats that data comes in. And last but not least is the veracity. Okay, so basically, when we talk about veracity, we are referring to the quality of the data. And I should say that, this property here is very, very important in the sense that, if you don't have, good or quality data, it doesn't matter the model that you apply. okay, to describe that data. It doesn't matter what model you use, you wouldn't obtain good results. Okay, so basically, veracity, it's one of the properties which is very, very important. And I think that, as, mathematicians or statisticians, if we want to analyze, any form of data, or if we want to develop a model to describe any data, we should also pay particular attention to the veracity, which is the quality of the data obtained. So basically, that is what big data it's all about, volume, velocity, variety, and veracity. So now that we know what big data is, and the fact that it's this complex data set which cannot be easily be analyzed by the traditional approaches, then you notice that depending on the type of discipline that you fall in, we have several kinds of data sets. So we have data sets from the sciences, from biology, from public health, and even for public health right now, you notice that we are now in a pandemic, so we now have data, which is the COVID data. We also have data from the financial industry. We have data from the meteorological services. We have several kinds of data, and the goal is that, depending on the type of discipline that you are in, the goal is to be able to, model some of these data sets. So then in this talk, basically the data sets that we'll be looking at is data from the financial industry. So here we are looking at, financial data set. And for that matter, we are narrowing it down to high frequency financial data. And I talked about high frequency, which is data which is generated second by second or minute by minute. We could also have nanosecond, but then I believe second, it's more it's more generic. Good. So now that we have all this data, then what comes to mind is that, okay, then what models have been utilized to
Also, quick question. Your slides are not moving.
Oh, really?
Yeah.
Okay, I think then it's lagging behind because I keep, moving back and forth. Okay. So what page is it right now?
It's still on the front page.
Oh, really? Oh, sorry.
Okay, now it's moved to the several deterministic and okay, now
Oh,
it's moving.
okay.
Okay.
It's moving now. Okay, then I think probably I might leave it like this. Okay.
Oh.
Yeah, then sorry, sorry about that. So several deterministic and stochastic models have been developed to describe, depict the mathematical modeling of major stock indexes. So basically, when we say a stock index, okay, I should mention that, we have what is known. So here the key word is major. And then, so I'll talk briefly about the US stock market, and then I also talk, about the Ghana stock market. So for the US stock market, we have, three major stock indexes, and one of them is the SP 500, which is also known as the Standard and Poor 500. So basically, the SP 500, it's a stock of, the greatest 500, companies in the US. So basically, what that company does is that, or what that index does is that it tries to give you an overview of how the major 500 companies in the US are faring. So then if you're an investor, then all that you need to do is that based on the trend of the stock index, then you can make informed decisions. So another stock index is called the Nasdaq. Okay, and for the Nasdaq, it's more about, so for the Nasdaq, it's list 3,000 companies, but then for Nasdaq, they are more concerned, with technology companies. So for instance, Facebook, Google, Apple, IBM, any company that deals with technology, that is what the Nasdaq, described. And then the last but not least is the Dow Jones. And the Dow Jones, it's also another stock index, but this time around, it just measures the 30 most, let me put it, important, or the 30 major companies in the US. So basically, these are the different stock indexes that we have in the US. Well, there are others, which for instance, the Russell 2000 or the Russell 3000. Okay, all these are stock indexes, but then the major ones are the one that I described. And also in Ghana, well, the two most popular stock indexes are the first one, which is the Ghana Stock Exchange, index, composite index. So basically, this index, what happens is that all the companies in Ghana listed on the stock exchange, this composite index measures the rate at which the market it's faring. And then another stock index is the data bank stock index, which is the DCI index. So basically, for the data bank, it also measures it's some of the companies listed on the Ghana Stock Exchange. So basically, the goal is this: when you have this stock, the stock index, as an investor, or as a practitioner, all that you're interested in is that you want to, look at the trend, and then based on the trend, you want to make informed decisions. Okay, so then if you're an investor, you are interested in making profit. So then you want to be able to find, the right time to purchase stock, or the right time to sell your stock, because that's what you're interested in. As a researcher, you're also interested in the different ways, okay, or how you describe the evolution of the stock, the stock prices. So one of the first models that was developed to describe the evolution of stock prices is the Brownian motion, and I believe we all know, most of you have studied the Brownian motion. So this was developed by Wilmot et al. In the year 1993. So basically, they used the Brownian motion to describe the evolution of the stock prices. So then based on that, based on the evolution, then as a practitioner, you have an idea of how the stock prices behave. Good. However, you see, the Brownian motion that was initially developed to describe this evolution, the Brownian motion assumes that there is an increment in the logarithm of prices, and also the prices follows the Gaussian distribution. So from theory, Brownian motion, it's a random, it's a stochastic process which follows the Gaussian distribution. And we all know what the Gaussian distribution is, the Gaussian or the normal distribution. So depending on the discipline that you are from, for instance, those in engineering and finance, they call it the Gaussian distribution, but then those in mathematics and statistics, they call it normal distribution. Good. So we all know the normal distribution, it's symmetric, which has light tails, and then the mean and the median lies in the middle, and it's symmetric in the sense that it's one half is the mirror reflection of the other. However, empirical studies shows that financial indices doesn't have that light, the light tails. And remember that for the normal distribution, okay, at the tail, that's where we are able to determine the outliers or the extreme event. That is, all the outliers happens at the normal tail. So for instance, if we are interested in modeling income, then you notice that majority of the people will their income is going to be in the middle. Why? Because most people, their income, it's more or less when you find the median, it's more or less at the middle. However, you notice that at the extreme tail, that's where we have, the super rich, and at the left, that's where we have the poor. I wouldn't say the super poor, but that's where we have the poor. So you notice that the poor and the rich, they are more or less the outliers, and then majority of the people will fall within the middle. Good. So then, so from the empirical studies, what happened was that whenever we try to, find the density distribution of any stock market index, we noticed that the tail is heavy. Okay, so what does that mean that the tail is heavy? So then what it means is that we have greater kurtosis. We have greater kurtosis. And then from theory, you notice that if the kurtosis of a time series is 3, then that is the Gaussian distribution. However, if the kurtosis is greater than 3, then it's not a normal distribution. Okay, so then if it's not a normal distribution, then we could say that it's a non-Gaussian distribution. And I'll talk about non-Gaussian distribution very soon. So we have several different types of non-Gaussian distribution. Good. But then for kurtosis, depending on the type of literature that you're looking at, some people compute kurtosis, so from the formula of kurtosis, if you subtract 3, then you could say that if the kurtosis is 0, then that is the normal distribution. If the kurtosis is greater than 0, then it's a non-Gaussian distribution. So basically, depending on the type of literature that you're looking at, we have different measures for kurtosis. Good. So basically, since the empirical evidence suggests that the normal, the stock indexes, okay, they don't follow the normal distribution because it has heavy tails. Then several, researchers have, developed models to describe, this new behavior, the heavy tail. Okay, and let me, give you a little background. Why do we have the heavy tail? So then you notice that for any distribution, the tails, like I, mentioned, corresponds to the extreme event. So basically, if there are a lot of fluctuations in the data set, and here, what do I mean by a lot of fluctuations? So for instance, if there is a sharp drop in the price of a stock, okay, so let's assume that the price was maybe 100 Ghana cedis, and all of a sudden it dropped drastically to 50 Ghana cedis. Then what happens? Then we have a sharp decline in price. So then when you have a sharp decline, this is known as a market crash. Okay, so then whenever you have a sharp decline in a stock, then we say it's a crash. Okay, so normally when you have this, fluctuations where there is this, sharp decline, then this, sharp decline, it's recorded at the extreme, at the extreme tail. So one of the models that was used to describe this behavior was the Levy model. And the Levy model is a non-Gaussian, process. Okay, so what do I mean by non-Gaussian? Meaning that it doesn't follow the normal distribution. Okay, so this time around, it's able to capture, the tail of the distribution. And the Levy model, which was developed by Marani et al. And Berani, they modeled, critical events. And here, what do I mean by critical events? So critical events are events that has a high, catastrophe on the people. So basically, we could have several, critical events. One of them could be a financial crash. Whenever there's a financial crash, then it's the people who have, significant loss. One other critical event is also an earthquake. An earthquake is also a critical event. And even in this current time, we could say that, the COVID-19 is also a critical event. Good. So, and one other model that was used to also describe, the evolution of the time series is a model by Linet et al. In 2008, where they used long-term correlations to explain the fluctuations of magnitudes of, or the interoccurrences of high-frequency time series events. But then, from all these, papers and works that has been done, there seemed to be, one major drawback, and one of the major drawback is that it's either that, model developed is not, it's not completely stochastic. Okay, and what do I mean by stochastic? So basically here, this figure here, we have, so on the left are two dots, we have, so basically this figure, we have two, figures here. On the left, you notice that these dots are uniform, they are fixed, correct? We have uniform fixed, and you also notice that the spacing are equal, more or less. We could say that these are evenly spaced, okay? But then on the right, you notice that these dots, they are non-uniform, correct? They are, placed, randomly. So that is what we mean by stochastic. So if we say something is stochastic, then what it means is that it's random. You cannot easily observe it. Okay, there is lots of fluctuations, and for that matter, we have a variable dot spacing. So that is what we mean by a stochastic pattern. Good. So some of the models, because the data sets, we can describe the data to be a stochastic process. The data itself, for instance, the stock market data, there are lots of fluctuations. So since there are lots of fluctuations, the data points are not easily observable. So because they are not easily observable, then you need to be able to take that property into consideration when you are modeling this. And another thing is that some of this model does not take into account the physical behavior of the time series. And what are the physical behavior of the time series? So one of them is the fact that how the data evolves over time. Okay, so if you include that property into the model, then you are able to obtain a model that can correctly and accurately model that process. So basically, in this talk, we will discuss the model that will enhance the understanding of extreme event. And I already explained what I mean by extreme event in data science, statistics, and related fields. Okay, so and I should mention that even though in this talk I'll be presenting on the financial aspect, we can apply this technique to several other data sets. And the proposed model offers analytic flexibility and also provides a continuous time process which is capable of exhibiting long memory behavior. And I will explain what it means that for a process to exhibit long memory behavior. And then one advantage is that the model that I'll be discussing, it's a mean reverting jump process. Okay, and here the keyword is jump. So why do we have jump? We have jump because for the financial data set, because of the fluctuations in stock prices, so we describe these fluctuations as a jump. Okay, the fluctuations in stock prices, we describe this fluctuation as a jump. So it's a mean reverting jump. And what do we mean by mean reverting? So what mean reverting means is that at the long run, okay, the price will move towards its mean value. So then that's what it means to have a mean reverting jump process. So mean reverting in the sense that the price moves towards its mean value. And this mean reverting jump process is able to describe the unique, dependency in a sequence of events. And this model has been used by Bendorf and Shepard, to describe market volatility. So basically, what is our goal? So first of all, the first goal is that at the end of this talk, I will discuss the Einstein-Uhlenbeck stochastic differential equation, which is, a model that is used to describe several time series. Okay, and also we will also estimate some parameters. Okay, and these parameters are useful for making inferences, and also they are useful for predicting this type of event. And then based on what we obtain, if you're a practitioner, or if you're a stakeholder, based on the parameters or based on our work, you'll be able to discover that a crash is imminent and then take the necessary precautions. So you see, it's always good to be prepared than not to be prepared. For instance, if you're an investor and then based on the evolution or the trend of the time series, if you notice that there is going to be a sharp drop, then if you're an investor, then it's good that you sell your stocks so that you can make some money. So then that's from the financial point of view. If if you're a public official, so for instance, if maybe you are interested in modeling the evolution of the COVID disease, we can describe the evolution or the path. So if you're a stakeholder or the government, based on the evolution, you can take the right precautions. Okay, you can take the right precautions, and then you can inform the public on the things to do. And you see, some people argue that since it's random, okay, since the process is random, you cannot correctly predict. Fine, but then you see, if you have an idea of the path, okay, once you have an idea of the path, it's good that you take the precautions, than you not taking any precautions, then all of a sudden you have a critical event, and that's not good. So it's always good to have an idea of how the time series evolve over time. And then last but not least, we will also be able to analyze the effect that event that happened in the past have have an effect on present and future events. So then you are looking at past, present, and based on the past and present, you want to be able to talk about the future, or more or less want to forecast into the future. Good. So now this is the model that we are looking at. So we have the one-dimensional Einstein-Uhlenbeck model. So here the Einstein-Uhlenbeck, we have the shorthand OU. So whenever I say OU, I'm referring to the Einstein-Uhlenbeck model. So here here we are defining a stochastic differential equation. Okay. So for on the right-hand side, okay, you notice that we have two terms. So then if we get rid of the second term here, then we just have a deterministic. Okay, we just have a deterministic model. So that becomes an ordinary differential equation, Good. So because of this random term, that's why this is known as, that's the stochastic component. So that's why this is known as a stochastic differential equation. So then if you have a differential equation, how do you solve it? So basically, depending on, we are looking at, so remember, if you get rid of this part here, okay, the stochastic part, then we have a first order ODE, correct? First order ordinary differential equation. And how do you solve it? So depending on the type, whether if it's exact or not exact, if it's not exact, you have to multiply through by an integrating factor, and you perform all those techniques. We use a very similar idea to solve this stochastic differential equation here. So in order for us to solve, we have to multiply through stochastic differential equation to make it exact. And once you multiply through the stochastic differential to make it exact, then the next thing you do is that we apply what is known as the Ito lemma. Okay, so once you apply the Ito lemma to that differential equation, then you differentiate. And after you've differentiated, you integrate both sides of the equation. And once you integrate both sides of the equation, we have the solution. So basically, this is the solution of our stochastic differential equation. And then, so for this stochastic differential equation, this is an Einstein-Uhlenbeck. And here it's Einstein-Uhlenbeck because of this constant here, the negative lambda. So here, this value lambda here is known as the intensity parameter. And so here, this intensity parameter is basically the mean reversion rate. Okay, and I'll talk about that. So basically, whenever you have this stochastic differential equation, then the goal is to be able to estimate, this, parameter here, lambda. Good. And now, so for every stochastic differential equation, since this part here is the random term or the stochastic term, then this stochastic term should follow a process. So initially, this term here followed what is known as the Brownian motion. But I explained that the Brownian motion, it's Gaussian. Okay, and for that matter, empirical evidence suggests that the data set itself has heavy tail. So because it has heavy tail, then we need a non-Gaussian process. So here we call this the background driving levy process. So in shorthand, we say it's the BDLP. And I should say that the levy process is a non-Gaussian process. Okay, and we have several, we have different types of levy processes. And one of them is we have the compound Poisson, which is the levy process. We have the inverse Gaussian. We have the gamma process. So we have different types, So basically, based on the data sets, because you see, the goal is that we want to be able to describe our data sets. So in order for us to describe our data sets, we need to choose, a BDLP that takes into account the behavior of our stochastic, process. So here, basically, this is our stochastic, process. So here we'll be modeling our time series, using this process. And one property of this process is that the background driving levy process, it's an increasing process, okay? And because it's an increasing process, also the initial condition is such that x naught is greater than 0. So therefore, since it's an increasing process and our initial condition is positive, then our solution, this stochastic process here, is strictly positive. Okay, so then that's something that we need to mention. Good. So now that we have, so here I will say that this is the one-dimensional Onsta-Unlubeck model. Now, we want to, include correlation structures, okay? And we know what correlation is, the strength of relationship between two things. So basically, for the time series, that is the financial time series, we noticed that, the data points are such that, when you find the autocorrelation, okay, the autocorrelation function between, 2 points are very, it's high, the correlation is high. So because of that, if we have some high correlation in the data set or the data points, then we want to include this correlation structure in our model. So then how do we include that? So basically, we included this by looking at the superposition of several OU processes. So this is what we have by the superposition, and here it's a weighted sum. Okay, and here the condition is that the weight should sum up to 1. Okay, so basically we are looking at the sum of m independent processes. To make our life very easy, let's just consider a very simple case. Even though it's simple, but it's simple and complicated case. Okay, so here we are looking at a 2-component model. So for 2-component model, we are looking at the sum of 2 independent OU processes. So for all these 2 OU processes, we have weights W1 and W2, and then the sum is greater. The sum or the weighted sum is 1, and also each of this also follows the follows the BDLP, which is the background driving levy process. And then because we are looking at 2 different, the sum of 2 models, then you notice that here we have 2 parameters. We have negative lambda 1 and we have negative lambda 2. And as usual, the initial condition, so here this, x1 and x2 corresponds to the initial condition. So since this is a strictly increasing process, then here the condition is that x1, x2 should be greater than 0. Good. So now once we have this superimposed OU model, then the goal is that we want to be able to approximate. So then how do we approximate the solution? So basically in approximating stochastic differential equations, we have several methods. Right? So here we utilize what is known as the Maruyama model, or simply put the Euler model. So here, this Euler scheme, it's very similar to the Euler method for approximating ordinary differential equation, first order ordinary differential equation. So here, this Euler method is obtained by truncating the Ito's lemma of the stochastic Taylor process. Remember, when you are solving the stochastic differential equation, you need to apply the Ito lemma. So then once you apply the Ito lemma and you truncate after the first order terms, you are able to obtain the Euler scheme. So basically, the Euler scheme is what we use to approximate stochastic differential equation. I should mention that we have several schemes. We have the Euler-Milstein scheme, and the good thing is that because of the fact that this model takes into account the extreme event at the tail, it doesn't really matter which type of scheme that you use. The result doesn't deviate so much. And here for this scheme, this converges. It's with strong order of 0.5 under the Lipschitz and bounded growth condition. Good. So now we are going to talk about the gamma process. And why do we have to talk about the gamma process? Because you see, we mentioned that the BDLP of stochastic differential equations follow the Levy process, correct? So since it follows the Levy process, then we need to define the exact Levy process. So basically, the process that we are defining is the gamma process. So then what's the gamma process? So here, basically, the gamma distribution is defined to have this probability density. Okay, so here we have two parameters for the gamma distribution. We have A, which is the rate parameter, and we have B, which is the intensity or the shape parameter. So basically, these are the two parameters. And very soon I'll talk briefly about what each parameter does. Okay, so this is the probability, the probability distribution of the gamma process. And then, so now that we've defined the gamma process, so here we are, saying that our BDLP, which is the stochastic, part, the stochastic term of our stochastic, differential equation is driven by a gamma distribution. And that is, if you say that it's driven by the gamma distribution, that is a huge statement, because you see, if it's driven by the gamma distribution, then what are some of the properties of the gamma distribution? One of the properties of the gamma distribution, is that it is a compound Poisson process. And here, what do I mean by compound Poisson process? So for compound Poisson process, you notice that a Poisson process, describes interarrival times. Okay, so then meaning if it's compound Poisson process, then we are looking at the summation of several interarrival times. And one of the properties of the compound Poisson process is that because we're looking at the interarrival times, okay, the time at which an event occurs, then there are lots of jumps. Okay, so because there are lots of jumps, this compound Poisson process jumps a finite number of times in a compact interval. So here, what do I mean? So meaning that, you see, when you have, when you are given a time frame, okay, within that time frame, there are lots of, for each, interarrival time, okay, when an event occurs, within that compact time frame, you have several jumps. So here, these jumps, in our case is, the fluctuations in our data sets, okay, the fluctuations. So the fluctuations is captured by the compound Poisson process. And then, so because the compound Poisson, the gamma process is a compound Poisson process, then we can make an inference that our gamma OU model also jumps, within a finite number of times, we have find out what jumps in that compact interval. Okay, good. So then therefore, because we are, taking the BDLP to be the gamma process, we call our model the gamma OU model. So whenever you hear the gamma OU model, basically it is the Einstein-Uhlenbeck model that I explained earlier on, where the background driving levy process is a gamma process. Okay, and it's a gamma process because we want to take into account, the jumps. It's very important that we are able to capture that jumps, that fluctuations, and we capture that by introducing the gamma process. Good. So now that we have our model, which is the superimposed gamma OU model. Remember, we are looking at the two-component model. So since we have it, then the goal is that, okay, then we need to estimate our model parameters. So here, what are the model parameters? So remember, for the gamma model, we have parameters A and B, correct? And then for our stochastic, model, we have two parameters. We have lambda 1 and we have lambda 2. So then these are parameters that we need to estimate. So first of all, we consider the gamma, the A and B. How do we do that? So we estimate, these values by looking at the theoretical moment of stochastic process. Okay, so here we define a proposition. Okay, good. So then for this proposition, it says that whenever you have a levy process, okay, then for levy processes, we know that the expectation, of that process at the at time t equals to 1, it equals to the mean, and we know that the mean is finite, and also the variance of that stochastic process is also finite. Good. So then if it's finite, then we have for our stochastic process. So here the stochastic process corresponds to the solution of our stochastic differential equation. So here the expectation of our stochastic process, for our stochastic process, is equal to mu, and then the variance is also equal to sigma squared over 2. So then therefore with this properties, then we can use theoretical moment to calculate to estimate the values of A and B, and it's obtained. So here this corresponds to the estimate. So here, this, after a little bit of algebra, you obtain this to be our estimate. And then the next thing that we do is to also estimate intensity parameter, which is lambda. Okay, and here this is very interesting, because I think that the algorithm that we designed is very efficient. Okay, so here basically for this algorithm, what we did was that since we are looking at a two-component model, remember, I explained that we are looking at the superposition of two Einstein-Uhlenbeck models. So for this Einstein-Uhlenbeck model, this corresponds to, so we have the sum, and then the autocorrelation function of this stochastic process is defined by, by this. So basically here, this corresponds to the autocorrelation function. And since we are looking at the sum of the weighted averages of this, then we have this equation here, correct? And then here we are just using a different conversion. So here basically what we are saying is that we can rewrite this term here, to be like that, correct? And then where C1 is defined as the exponential of negative lambda 1, and C2 is defined to be the exponential of negative lambda 2. So basically it's just it's just the same thing, just that we've rewritten it. And the goal is that we want to be able to write it in a way where we can easily solve it. So basically here, in order for us to derive the solution of lambda, okay, of the lambda, what we do is that here we define an operator T, but this operator, we call it, the time shift operator. So here, what it means is that when you perform that operation on rho, so basically here, rho is the autocorrelation function. So when you apply the transformation on rho, then it's shifted by 1. Remember, I mentioned that here T corresponds to the time shift by 1. Good. So basically, once we have this time shift, then basically what we do is that we find, we can define another operator, which is T minus C1. Then once we have T minus C1, we perform that operation on row. Okay, so we find T minus C1 and then we find T minus C2. So once you perform the operation of T minus C1, so remember C1 corresponds to this definition here, and C2 also corresponds to that. So once we find T1 minus C1, we perform the operation on row, and we also perform the same operation on T1 minus C2. We obtain this, this equation here. And the interesting thing is that, so for this operation, remember, so we are performing, for each operator that we define, we shift it by 1. Okay, so after you perform, all the shifting, you get rho k plus 2 equals to A rho k plus 1 minus B, where A and B are defined by, A is defined to be C1 plus C2, and B is defined to be C1 dot C2. So here it's the product. Okay, so we are looking at the product. Good. So now once we have this, then it's very simple. We can, so once you have this, then if you know the empirical values, of equation 7, yes, and here you can obtain this empirical values from data. So once you have your time series data, you obtain the empirical values. So once you have the empirical values, then you can solve, and from A and B, we can solve for C1 and C2. So here, for instance, you could make C1 the subject and then plug it here. So then if you plug it here, then we can have C1. So if we make C1 the subject, then we can plug it here. So here, in place of C1, we have A minus C2 times C2. So then if you solve it, that becomes the quadratic equation. So once you have that quadratic equation, then you can solve for the solution of that quadratic equation is given by this, is given by this model here. So basically, the whole goal is that if you solve for A and B, then you can plug it here to get C1 and C2. And remember, once you obtain C1 and C2, then you can obtain the values of lambda 1 and lambda 2. So I think this is a very interesting algorithm that we developed. Good. So now the next thing is that we now want to simulate. So now that we have all our model and we have the parameters and everything, then we now simulate our model. So basically, this is the process to simulate our model. Good. So a MATLAB module was developed to simulate this process, and we simulated independent parts of our model using different time steps. Good. So in this work, we'll be looking at two set of applications, and in order for us to also investigate our model fit, we'll be computing what is known as the root mean square error of the time series. So here, the mean square error, compares the actual time series with our simulated time series. So we want to compare between the two and how it behaves. And also, this is, excuse me 1 minute. Okay, and also the rate parameter, which is the A and B from our gamma process, it controls the rate of jump arrivals. Remember, it's very important that we are able to control the rate at which the jump, the time series fluctuates. And also the shape or B describes the jump size of our time series. And the two parameters, which is lambda 1 and lambda 2, measures how the model reacts to perturbation. So here, perturbation talks about, if there is a small change, how the system behaves, if there is a change. Good. So now, so for our first application, we'll be looking at the Bernstein's collapse. So basically, the Bernstein's collapse was a market crash which occurred in the year 2008, and you notice that for 2008 that was known as the global financial crash. So basically, for this, what we did was that we wanted to analyze, some stocks from, high corporations. So basically here we considered the companies considered Bank of America. So here this is one of the banks in the US, and also Disney. So here we also looked at the entertainment industry, which is Disney, and then the JP Morgan Chase is also a financial, institution in the US. So basically these were the three companies that we looked at. Good. So here, so basically in this graph, we can see, the evolution. You notice that here, this part here, you see the sharp drop. Okay. So this, corresponds to, one of the crashes. Okay. So you notice that there are so many different crashes in this time series, data. So then the goal is that we want to be able to, we want our model to be able to describe, this fluctuation. So this corresponds to a minute by minute. Okay, so here we looked at, high frequency in the sense that we looked at minutes and we looked at seconds. So we also have that for the second, and you notice that for the second we also have, a lot of fluctuations in the data set. Good. So here, the first thing that we did was that we computed, our model, the parameters, and here you see here we showed the parameter for lambda. So basically we looked at the minute by minute data set, and we also looked by the second by second data set. We wanted to see how our model our model describe these two kinds of, so remember it's the same time series data. The only difference is that one of them was obtained minute by minute, and the other one was obtained, second by second. So basically so here you notice that the estimates of our second by second, it's pretty small compared to that for the minute by minute. Okay, and I will explain what that means, shortly. And then let's also look at, when we simulated our data. So here, when we simulated our data, we compared, the two. So here we noticed that the root mean square error for the second by second, it's really relatively small compared to the minute by minute. Okay, so here, what does that mean? So here, from this, then we noticed that, okay, then truly, our model is able to even capture more of the second by second, because of the high frequency nature. Because you see, if it's second by second, then it's more frequent compared to minute by minute, the rate at which the data is generated. So here we noticed that this model, performs very well with the second by second, even more compared to the minute by minute. Good. And then we also did, we also wanted to, see if indeed, what we are seeing was true. So here we also considered another event, which is known as the Lehman Brothers collapse. So here, this is also a financial, it was a financial crash that occurred in September 15, 2008. Okay, and we obtained this data from, the Thomas Reuters tech history, which is now known as the Refinitiv tech history. So basically, here we also considered, we considered 4 companies. So we also considered, the financial industry, which is Bank of America, JP Morgan Chase, and then we also considered the technology industry here, the International Business Machines Corporation, which is also known as the IBM. We also considered that stock, and then Walmart. So basically, Walmart it's a consumer, where they sell groceries. Okay, so in Ghana, we could say that Walmart is like, one of the big grocery stores, in probably at the Kaswa, is it the mall? Okay, yeah, the malls, Accra Mall or the Kaswa Mall, one of these huge markets. Okay, at those places. So here, we also showed the RMC when, because you see, from our first, work, we noticed that the second by second produced very good results. So here, we use the second by second, and then the results are, are very promising in that, we are able, the difference between the actual realization and our simulated data didn't deviate so much. So here we showed, the evolution, of our simulated part. So here, so for this part here, what we did was that we simulated, several parts, and then we found the median. Oh, sorry, not the median. We found the mean. So for the mean, what happens is that from the mean reverting process, it says that the process moves towards its mean value in the long term. So since it moves towards its mean value in the long term, that was why so basically, if you're an investor, then this gives you an idea of the path of the stock market. Okay, so if you're an investor, then based on this part, you can make some informed decision. So you can simulate more data sets into the future just to have an idea of how the path looks like. So basically, in this work, we used the superimposed on Stahlenberg model, and we compared, we used the Stahlenberg model to describe the evolution of the time series, and then the superimposed OU model is a weighted sum of solutions. So here the weighted sum takes into account the correlation structures, and then we applied this on our stock, two stocks, two different market crashes, the Bernstein's collapse, and also we applied it on the Lehman Brothers collapse. And here we saw that the superimposed on Stahlenberg model captures.
Kofi, quick question. Please, can you do the presentation again? Can you show the slides? I think someone clicked something, so the slides are no longer showing. So if you can present now, then we can see the slides again.
Okay, sorry. Okay. So can you see it? Can you see it now, please?
I can see it, so I think maybe I'm hoping the rest can see it.
Okay. Good. Okay. So we looked at the Bernstein's collapse, and then this captures, the high frequency nature of our time series. And here, the good fit obtained, shows that our model is able to capture the high frequency nature of the data. And also, our model took into account the physical behavior of our data set, which is very, very important. So here, we've implemented flexible classes of processes that incorporate long-range dependencies. And this long-range dependency is capable of describing some of the key features of a typical time series. And here we looked at a time series in finance, and we can apply this to several several disciplines. And here we show that the stochastic differential equation, which is arising on the superposition of independent OU process, takes into account the physical behavior of the data. And the proposed model captures more realistic dependency structures in the sequence of events. And then one thing is that the results obtained will give an idea of the statistics of the future stock, path. So then if you're an investor, who lacks insider information, okay, but then have at your disposal all the information contained in the equity prices, you can, based on this, you can take all the necessary precautions, okay? You can take all the necessary precautions, and then if you also want to make money, you can describe, based on the evolution, you can have an idea. And our stochastic differential equation used is, capable of exhibiting long memory behavior. And here, long memory behavior means that current information is highly correlated with past information. So then this facilitates prediction. And this study reinforces the previous studies, by Mariani and Liu 2006 and Barani et al. In 2011, where the authors concluded that the generalized Levy models are very suitable to describe critical events, including financial crashes. And because the solution of our stochastic differential equation is a Levy model, the good fitting reinforces the previous conclusion. So the future work is, is to be able to use this model to also describe, the Ghana Stock Exchange, and also it will be good if we can, investigate the time the time that an awareness should be raised, for a market crash. And one other interesting thing that could be done is that we can also use this model to model the time evolution of the COVID cases in Ghana, so that the government and stakeholders can make informed decisions. And so this work has been published in about 4 places, 4 reviewed journals, and these are the references. And thank you so much for your time. So thank you, and questions.
All right, thank you very much, Kofi. This has been nice and fantastic.
Thank you.
So please, if you have any question, you can unmute yourself, raise your hands, and then ask your question. Okay, so Dr. Koko will ask a question. Doc, please unmute yourself and then ask your question.
Okay, Kasa. Kasa.
Can you hear me, please?
Yes.
Yes. We
All
can
right.
hear you.
Thank you very much for your most exciting and entertaining presentation. I saw these positions. If I just want to check my understanding, were you taking converse combination or just any combination?
Yeah, so I was taking converse combination.
Because I didn't see you indicating signs of the weights.
Yeah.
Did you also look at how to estimate those weights?
Yes, exactly. So if let me go back to let me share my the slides once more.
Sorry, it could be that maybe you showed it, but I got distracted at some point. Somebody.
Yeah, no problem. I will share right now.
He'll share it again.
Can you see my screen now?
No, we cannot. I cannot.
I cannot.
Go to the present now.
Oh, even if don't worry. Maybe you. I
want to explain it. I think that part it's also interesting. So let me. Okay. Can you see now?
It's loading now.
It's loading. Okay. Yeah.
Okay, good. Okay, so now, so you see, this is, the model, correct? This was the equation that we looked at, right? So then if we are able to, remember I explained how to obtain the lambda, right? So this was the equation I used to, obtain the lambda, which is C1 and C2. Good. So then if we are able to obtain C1 and C2, C1, this is C1 and this is C2. So if we are able to obtain it, then we can we can find this value here, lambda 1 and then lambda 2, correct? And then for rho of k, this is, we can get rho of k from, from our data, because this is the autocorrelation fraction. So once we know this empirical value, then we can estimate W1 and W2. And remember here, W1, since we are looking at, the weighted sum, the sum is W1 plus W2 equals to 1. So therefore, if we find W1, then we can obtain W2.
All right. Thank you very much.
No, you're welcome.
Any other questions? All right. It looks like there are no other questions. So Kofi, maybe after when everybody logs off, we can just have a quick chat. My main interest was, you presented one equation. So is it possible to extend to a system?
Yes. Well, actually, yeah, that is an ongoing work. Actually, the paper is ready and it's about to be submitted. So we looked at, we looked at a system of, OU processes, and basically, and basically the goal was that I wanted to see if there are, dependencies. So for instance, if you have, two stock indexes, right? I talked about the fact that we have the Nasdaq and Dow Jones. Okay, so if you want to compare these two, we want to see if there is any correlation, because you see, if we are looking at system, then we are coupling the process, right? So we want to see if there are some correlation between the structures. So that's one of the work that we've done. So we want to compare if the evolution of one time series from one stock index has any relationship on another. Okay, and also this is from the financial point of view, but then if we're also looking at maybe from the geophysical point of view, so suppose maybe we have an earthquake, right? So let's assume that maybe some places have earthquake prone areas. So one of those places is in Japan. Okay, so for instance, if an earthquake occurs in one geographical area in Japan, we want to model if, suppose we have two different places, we want to model if the occurrence of one earthquake in one locality has, an influence on another locality. So then that's some of the things that, we are looking at.
Oh, that's fine. That's really fantastic.
Yeah.
That's fantastic. All right. So, okay, if there's no further questions, then thank you very much. And some people have been asking for your slides. So if you make them available, I've also put them on the site.
Okay.
On our site, so that they can always go there and just read it or download it and have a view to help them develop themselves. But this is very, very nice. And we are excited for this. All right.
And thank you so much.
So the next talk is also next month, and we'll be listening to Professor Tweneboah from Norway, and he'll be talking about mathematics in industry. So he will talk about some Navier-Stokes problems in industry with regards to oil and gas, and then maybe to other industrial sites as well. So you can just sign up to the website, and then anybody who is interested can have a view, whatever they want. All right, so thank you very much, and then see you next time.